Okay. So, in today's class we look at solutions to the equation of radiative transfer. As you can very well imagine, radiation RT is that is radiative transfer equation is very formidable, it is very difficult to solve. Particularly the left hand side has got a simple di by ds, but do not underestimate that. Right side there are a lot of scattering terms, and if the scattering is not the same in all the directions, you have to use what is called anisotropic scattering, and the scattering varies with the size of the particles vis-a-vis the wavelength of the radiation which you are considering, right. So there is a what is called the r by lambda or d by lambda parameter, okay, size ratio parameter is there. Depending on that you can have a Rayleigh scattering, you can have Mie scattering, you have to use geometric optics and so on. So it is very highly, as I told you in the one of the earlier classes, it is a highly specialized field, very few people work in that. Most of the engineering gas radiation is well understood, but astrophysics, study of planetary atmospheres, using satellites to remotely measure rainfall, and using satellites to remotely capture the track of a cyclone, then using satellites to infer the atmospheric profiles, and then reconnaissance applications, military applications, spy satellites, so many other technologies. This will be read into what happens to this radiation is very important. Even your simple night vision camera used by army is based on the infrared. Say similarly the swine flu detection in the airport is based on infrared, which is emitted by, so a person having fever will have more surface temperature near the nose, and there are certain portions. Then they have a standard template, they will compare it with the reference benchmark. If it is off beyond a certain limit, then he is suspected to have swine flu and so on. Okay. Even your CAT scan, the CT scan, and CT scan is basically looking at X-rays and then looking at 3D. We take the pictures in various slices at various sections, and then we reconstruct a 3D image based on that. And so tomography, okay, that computerized axial tomography, that is CAT, it has become CT scan and all that, very advanced numerical method, advanced radiative transfer and all that, alright, and non-destructive testing, ultrasonics, lots of applications, right. Now we will, because it is only a first level course, we will look at a simplified treatment of the equation of transfer. We look at a one dimensional, we look at something where we do not worry about spectral effects, we do not consider scattering and all that. A very simplified solution for this was what we considered in the last class, where I completely knocked off the emission term and I told what happens to radiation which is absorbed, okay, by a layer of water or what in ocean and all that, what happens in the sunlight as it reaches the bottom and so on. Now we will formally look at some solutions to the equation of transfer, and it will lead to some complicated integrals which we will see as we go along, right. So this is basically you are considering a black wall, okay, basically I am starting with black wall to, otherwise that radiosity other things will come and it will be epsilon sigma t to the power of 4, it will lead to other problems, reflection component will be there and so on. Now the temperature is Tw, there is a gas layer, a plain gas layer, and not plain glass layer, okay, it could be glass but this is gas right. Thickness is L, it is infinite in the direction, in this direction is infinitely deep in the direction perpendicular to the plane of the board. So essentially we are looking at how I or the intensity varies in the direction x. X I have given somewhere, no, okay, so this is x, positive direction of x, that is the positive direction of x. The gas is at a temperature Tg, the wall is at a temperature Tw, okay, and the gas is going to absorb and emit radiation, so it is gas radiation, okay. Now we want to solve the equation of transfer. By solving the equation of transfer we want to find out how I or the intensity propagates with x, correct, that is the goal. So we have to write down the equation is already known to us, so di lambda by ds plus kappa lambda I lambda equal to kappa lambda of Tg, did you write like this? Correct. So this is 1. So this is for the normal direction. If yes, is oriented at an angle theta to dA. Look at path 2 on the figure. So the equation gets modified as cos theta, we have needless to say, when theta equal to 0, equation 2 reduces to equation 1, alright. Now we have to find out the story at the radiation arriving at an element dA, which is located at a distance L, the gas layer thickness is L, okay. Therefore the radiation arriving at A consists of two components. One is the radiation from the wall, which is sigma Tw to the power of 4 by pi, that is the I. Q will be sigma Tw to the power of 4, I will be sigma Tw to the power of 4 by pi, which is going through the gas, gets attenuated, that means its strength is reduced because the gas is absorbing or participating in the radiation and it is arriving here. Then there is also separately, there is a component because of the emission from the gas which is also arriving here, okay. There is a transmission by the gas, okay, and there is emission from the gas, alright. So let us consider an area element. Now let us simplify this. Let us say that dI for a plane gas layer, dI plus dx I have done several things here. Can you tell me 1, 2, 3? I have done several things here. I am assuming that the gas is gray, first point, yes, because I knocked off kappa lambda and put it as kappa, okay. So kappa is equal to kappa lambda. Second, I am using something called I plus. What does it mean? I am looking at the positive direction of x, okay. So what else? I am replacing the IB lambda by IB by sigma Tg to the power of 4 by pi, okay, nothing spectacular, there is nothing which was applied which we did not know, okay. Now we can we solve the equation of transfer for the straight path and then we will infer what the solution will be for the slant path, okay. So let us try and solve equation 3 for the straight path. The solution to 3 consists of two parts, namely the complementary function plus the particular integral. The complementary function is obtained by setting the right hand side equal to 0 in equation 3, right. Let me do that. General solution to get the complementary function. I also made one more change, I am using x, right, instead of s, right. The original equation had s, I am using x, that is okay. This is right, I plus, is it? I hope all of you remember this one way of solving ODEs. You can set the right side equal to 0 and first get the CF and then you get the particular integral, okay. and then combine the complementary function and particular integral, get the general solution, apply the boundary condition and get the constant of the integration. Okay, as far as particular integral is concerned. Will you agree with me? The particular integral I plus equals sigma Tg to the power of 4 Tg to the power of 4 by pi is evident. How do you check it? Now put this particular integral back into equation 3. What will be the first term? Di by dx plus 0. Second term is k sigma Tg to the power of 4 by 5. Therefore, this is a particular integral to this problem. Therefore, the general solution consists of the sum of both the Cf and the Pi. Seven. Huh? How do you get A? What is I at x equal to 0? It is not sigma Tw to the power of 4. Be more accurate. I am not talking about E. By pi. Okay. At x equal to 0, I is basically that is originating from the wall. We are looking at this story. What is happening to sigma Tw to the power of 4 by pi as it goes through the gas layer. Okay. So at x equal to 0, okay. Now therefore I plus of x equal to is that okay? Is it fine? Jaideep, I just split the A into the collected terms with Tg common. Okay. Why did we start the exercise? We want to find out I plus at x equal to L. So we will have to obtain the expression for I plus at x equal to L. Any problem? What are the units of kappa? Meter inverse, L meter. So the product of kappa into L, the kappa into X frequently appears in radiative heat transfer. So it is called the optical depth, okay, K into L So if for two media the optical depth of one medium is higher compared to the other, what does it mean? Its capacity to absorb radiation is much more, correct. An optically thin gas is one in which tau is very small, that means it absorbs minimum. An optically thick gas is something which has got a terrific tau, little will emerge out of a optically thick gas, okay. But beware, optically thin or thick, the tau is dimensionless. You are also almost tempted to believe that tau should have the units of meter when I say optically thin, optically thick. Kappa has the units of meter minus, tau is dimensionless, okay. Now so therefore in general it is tau subscript L, so this is tau x, okay. So what is this ratio? I want to find out the intensity at x divided by the intensity at 0. What is the intensity at 0? Sigma Tw to the power of 4 by pi. If you do that, what we get is okay. This is a performance metric for the gas layer of thickness L. If Tg by Tw is much less than 1, that is the gas temperature is, if the gas temperature is 300 Kelvin and the wall temperature is 1500 Kelvin, therefore Tg to the power of 4 by Tw to the power of 4 is very small. What happens in the second term? And then this reduces to what? What does it reduce to? It reduces to the Beer-Lambert's law. Then all right, fine. So why should you always worry about the straight path? Radiation can arrive at that elemental area dA from other paths also, isn't it? So, but we didn't want to work with the general path and get into the mess. Now we worked out for a simple path 1, and then we can, by induction or inference or whatever, you can guess what this I plus will be for a slant path, okay. For a slant path, Yeah, I left the E. Yeah. You can check for the asymptotic correctness of the expression by substituting cos theta equal to 1. Okay. Now mu is equal to 1 represents the straight path. Mu is very easy to handle, okay. Normally in radiative heat transfer we use the mu. And also when you are looking at, did you study fin heat transfer? If you have a variable fin area, you will get the cos theta frequently. Cos theta comes frequently in several areas of radiation heat transfer. I am not sure about stress analysis and all that. Cos theta is an important fellow in many walks of life. Therefore, you treat cos theta as mu, and therefore sin theta can be treated as minus d mu. Sin theta d theta can be treated as, okay. Why am I worrying about sin theta d theta? Because I am looking at I plus arriving from all angles, and then for a hemispherical average quantity I have to find out integral over the solid angle. So I will get sin theta cos theta d theta d phi, then I can convert it into d mu. Once you have d mu, already you can expect that you got e to the power of minus e to the power of something by mu, d mu, all that, and then beyond a certain point it becomes unintegrable or non-integrable. It is not integrable. Then we have to resort to some tables. These are called the exponential integral tables, which I will introduce shortly. So this is basically the general, this is basically the solution to the equation of transfer. You can see that even for a simple case of there is only one wall which is black, there is a gas layer which is grey, and we are looking at one positive direction of x, it is quite formidable, but of course we can do it with chalk and talk. I mean we are able to do with pencil and paper. So the more difficult things we will have to program, okay. Little bit of complications we can handle. Now let us try to find out what will be the heat flux arriving at the area, elemental area dA. Is that clear up to this stage? Which one? I plus or? I don't understand. Yeah, but kappa is always there. Since kappa is a constant, I can call it as a function of tau x. What is the problem? I can change my variable, isn't it? If x is the variable, I multiply x by k and call it a new variable x1. I mean it is perfectly legal because k is anyway a constant. Now we have to worry about the heat fluxes. So the heat fluxes are a little more involved, okay. Now if you have to write the heat flux, okay, heat flux at x equal to 0, which is going in the positive direction of x, is given by sigma Tw to the power of 4, no problem. Q L plus will be IL plus correct. I am saying IL is a function only of mu. I am not having the function with respect to, I am not saying it is a function of x because I am specifically evaluating the integral at x equal to L. Once I have L, I can make a general x. Okay, let us not get confused. We should not, we do not want to handle so many variables at a time. Okay, right. Why can't this IL be taken out? IL is a function of mu, guaranteed, because we saw that tau x by mu and all that. Okay, so it cannot be pulled out of the integral. But if it is azimuthal, if you have azimuthal symmetry, then integration with respect to d phi, the azimuthal angle, can be done. So the first simplification is I will pull the d phi out and put the 2 pi. Can I do that? Okay, let us do that. So QL plus is it allowed? Is it allowed? Okay, and cos theta can. No, this is what?
It was correct, sir. Correct. It will come
No,
minus
but d of cos theta means
minus sin theta. Minus sin theta.
Cos theta ranging from 0 to 1.
it's not 0 to pi by 2. Cos theta ranging from so there was a minus was taken care, 0 to 1, everything is done now. Several things have gone into this, correct. The sin theta, only 2 things, correct. The sin theta was taken as minus of d of cos theta, therefore the limits were changed. For instead of, we swap from 0 to pi by 2 to pi by 2 to 0, and because it was instead of theta it was cos theta, we changed it to 0 to 1, and we pi by 2 to 0, again we swapped and we took care of the minus. Now instead of d of cos theta I can put it as d of mu. Okay, therefore QL plus equal to all right. Now we have to substitute for IL of mu. We have to substitute for IL of mu and try to accomplish the integration. As engineers, ultimately we are interested in the flux, so many watts per meter square. Why are we worried about watts per meter square, per micrometer, per steradian and all that? Okay, so we have to get this, right. QL plus equal to 2 pi plus correct. Okay, fine. Is that correct? Am I doing all right? I took the second term, huh? Huh? Yeah, is it okay? Have I written it out properly? Okay, now the first term therefore that is all plus 2 sigma, is it? 2 I can take the TL to the power of 4 Tg, it can be taken out. So, you get mu e to the power of minus tau L by mu d mu, it cannot be integrated, do whatever you want, do whatever you want. Integral u dv is uv minus integral v du, then it will e to the power of e to the power of e to the power of, it will give period, whatever, all your JE stuff will not work, none of it at all, nothing of it at all. So, the integral mu into e to the power of minus is an integral which frequently appears in radiative heat transfer, it is called an exponential integral, okay. So, what happened to there? I left a pi, is it? Okay, sigma so frequently appears in radiation. It is known as the exponential integral of order 3. Huh? Yeah, there is. Is that correct? What is minus? Huh?
TW minus TJ.
TW minus TG, is it?
Yes, sir.
No. Oh. Yeah. I don't want to write what I don't believe in. Let's see. So, what happened? T. Okay. Okay. Morning when I worked out at 5 o'clock, it was TG minus TW. I think I made a mistake. Okay. All right. Now, this mu e to the power of minus tau L by mu d mu frequently appears. It is called exponential integral of order 3. So, what does it mean? There are exponential integrals of other orders also. Okay. So the general exponential integral is given like this. okay, mu to the power of n minus 2 into e to the power of minus t by mu. That is a general exponential integral of order n. Mu is basically a dummy variable. Mu is basically a dummy variable. Okay, so this is what we got, right? So I think we are, this should be 20. Okay. The exponential integrals have been worked out and they are tabulated, and I am going to give you the table now. Yeah, please do the leftmost number has not come out well, it got cut in the photocopying, but it is all right. So this is the, you will take it, this is the exponential integral. You can see the first column gives you the value of x, the second column is E1, third column is E2, E3, E4. As far as this course is concerned, we are worried about the first column and the fourth column, okay. Okay, fine. What are the salient properties of this E3 as observed from the table? E3 of 0 is 0.5. Please check. So that means that t is very small. What is our t? Our t is actually tau, optical depth. So if the optical depth is very small, then this exponential integral reduces to half minus t, which is a great boon for us. So the limit where the t approaches 0, that means the gas is not so heavily absorbing, it is called the optically thin limit for radiation, okay. It is the optically thin limit, it is optically thin enough to allow that approximation, but it is not thin enough to neglect gas radiation, okay. One by 1 plus 10, the 10 is very, the 1 is very small compared to the 10, therefore 1 by 1 plus 10 equal to 0.1, but you cannot say 1 is very small compared to 10, therefore whole thing is 0. They are two different stories. It is like this, okay. It makes it handleable, and E3 of infinity at 3 point, what happened at 3.5 itself, it became what, 0.005, therefore E3 of 10, 20, 30 will tend to, okay, very good. So we have these properties. Now you can write the general expression for QL plus, can you write, therefore QL plus is sigma E3 of, that is all, E3 of correct. Oh no, I am making mistakes again and again. This is plus one minus okay, all right. Now what can you say from this? 1 minus, can you interpret something from this? Can you interpret something from this? Let me see. Okay. Now we will apply for the optically. Now 20 for the optically thin gas. What is E3? Half minus T. Therefore, this will be 1 minus 2T, yeah? One minus 2 tau L by 2. Plus tau L 2 tau L. Okay. The 2 is not leaving us, no? Okay, what is the big deal, man, now? What is the big deal? The radiation arriving at x equal to L consists of two parts: the radiation which is coming from the wall, which is attenuated by the gas, and the radiation which is directly coming from the gas. Fortunately for us, now we have an expression which gives two independent things. The first seems to concern the radiation from the wall, the second seems to concern the radiation from the gas. Therefore, this tau L can be, if we say this tau L is an equivalent gas emissivity, then the second term is epsilon g sigma Tg to the power of 4. What is that radiation which is emitted by the gas which is arriving at the elemental area at x equal to L. So this can be treated as the transmissivity of the gas. Okay. So no. What is the relationship between this? Tau g is 1 minus epsilon g, right? Epsilon g itself 2 times kappa into L is 2 times kappa, 2 times L into kappa. Now comes the killer stroke. Okay. For all this, the goal of anything is to finally simplify. The goal of anything is finally to simplify, right? Now at the end, we are able to define equivalent gas emissivity, which consisted of 2 parts, 2L into kappa. Intentionally I put 2L within brackets and kappa within brackets. The 2L is basically related to the geometry. The kappa is related to the capacity of the gas to absorb. Therefore, when I combine this geometric part and the thermal part, I am able to get an equivalent gas absorptivity, with which I can use my radiosity formulation which I used for the evacuated enclosure. I can modify it and use it for this. Okay. What is this 2L? This 2L represents the mean path travelled by all rays in arriving at the area element A, which was located exactly at a minimum distance of L from the wall, because for cos theta equal to 1 it will be just L, for all the others it will be L by cos theta, and the L by cos theta keeps changing. So this 2L is some sort of an average or a mean length which a ray travels before hitting this area element DL, area element DA. So this is called the mean beam length. So this is a terrific progress we have made in the last 50 minutes, that we started out with the equation of transfer and did all mathematics, exponential integral, but I did so many things. We did optically thin gas and all that. We arrived at now the formulation has reached a critical stage where the gas emissivity can be composed into 2 distinct parts, and the thermal part can be completely separated from the geometric part. Okay. So this 2L is the mean beam length for a plain gas layer. This mean beam length will change for a cylinder, for a sphere, and so on. So if you are able to calculate the mean beam length, and if you also know the kappa, you have a handle, you can calculate the equivalent gas emissivity, and then from the gas emissivity use this relation and calculate the gas absorptivity, and you can proceed further. Okay. In tomorrow's class we will see how we can use the theory of evacuated enclosure, modify this, and then solve problems of enclosures with absorbing emitting gases. Okay. Anyway, to reinforce our concepts and the solution of RTE, tomorrow we will solve 2 problems involving basic plain gas layer, and then proceed to the theory of evacuated enclosure. Okay. Thank you. I will just